Welcome to Chapter 1, Section 1 on graphs and functions. We're going to take a look at some of the basics, terminology, etc. that we use when we are looking at creating graphs to represent equations and relationships between variables. Some basic definitions that some of this you may be familiar with, some of it may be somewhat new to you, but an ordered pair is what we call something that involves two numbers, one representing x and the other representing y. When we put those together in parentheses with a comma in between, we call that an ordered pair. The first number always represents the horizontal axis on the Cartesian xy coordinate plane, and the second number always represents the y. And so as we're graphing points for our ordered pair, the x and the x dictates to us to move either to the right or to the left horizontally, and then the y tells us whether we're going to move up or down. Positive indicates in upward direction, down is negative. So if we're going to graph the point A at 3, 1, I'm going to first move to the right 3, I'm going to go up 1, and there's my point. Now I'm using a letter there, and I'm using these arrows, but the arrows are not really something we use when we're actually graphing. I'm just doing that for illustration purposes. B has a -2 followed by a 4, so that means we're going to move to the left 2, and then a +4 moves up 4 units. You'll notice here with A, I'm going back here a little bit, it's at 3, 1, and this is at -2, 4. This is our B point. In fact, the A point lies in what we would call the first quadrant, where both the x and the y are positive. B lies in the second quadrant, where if we're moving left first and then up, that puts us into quadrant 2. So x is always negative, y is always positive. The third quadrant moves to the left, and so for the third quadrant, both the x and the y are negative. And so that brings us to C here, point C, -3 and then -4, puts us in the third quadrant. And then the last point, or not, I'm sorry, it's not the last point, but 2, -3 is our next one. 2, -3 puts us down here. Let's see, this one was C, so this one is D. This is actually the fourth quadrant because we moved forward and then we moved down. So x is always positive, y is always negative. And then our very last one is -3, 0, which puts us right here. This is point E. Whenever we have a 0 with either the x or the y, that tells us that we are on one of the axes. In this case, E is a x-intercept. Okay, now what we're going to look at is how we can find the distance between two ordered pairs that we have on the Cartesian plane. And we do this using the Pythagorean Theorem, which you may be familiar with, but it's when we take the two sides that come together at a 90-degree angle, so we have a right triangle. The two sides that come together are called our legs, and the third side is called the hypotenuse. And what the Pythagorean Theorem shows is that if we take the sum of the squares of the legs, that it will always be equal to the square length of the hypotenuse. Now we're going to use that here for what we call the distance formula. And I put some stuff here so you can kind of see the similarities. D, which is the distance of our line, is kind of our C. It's our hypotenuse. And it's notice that it's C and not C squared, and that's because we have the square root over here. So we've taken the square root of both sides of this equation, and then we're left with the sum of the squares of the two legs. And the two legs end up being the horizontal and the vertical distance. So x2 minus x1. Whenever we subtract two numbers, you're going to see what we're finding is the distance between those two numbers. So by going x to the second x minus the first x, we're finding the horizontal distance, and the two y's subtracted give me the vertical distance. Those happen to be the sides of, which would be the legs, so the sides that come together at a 90-degree angle. Let's take a look from an actual example here. So I've got 2 points here. The first one's at negative 2, 5, and the second one's at 3, negative 4. And I kind of overshot my point there a little bit. All right. So looking at the line here, if we want to find this distance, I'm going to draw out. Now this is just for our visual sake here. This isn't necessary in order to use the formula. Whoops. Now that happens. Let's go ahead and erase that. So I have negative 2, 5. I'm just going to go ahead and mark that here. I've got 3, negative 4. And then this point here is x-wise, it's at negative 2, and y-wise, it's at negative 4. Just putting that in there. Okay. So if we look at the height, let's just look at it from a triangle perspective. I'm at negative 4, so from here to here, that's a distance of 4. And then we're going all the way up to 5, so that's a distance of 5. We can see the length of that is 9. And then from negative 2 to 0, that's 2. And then from 0 all the way to 3, that's 3. So the distance here is 5. So I'm just going to go ahead and write out the distance formula. Distance is equal to the square root of the two x's subtracted squared and the two y's, difference of the y squared. I'm going to take the square root of the whole thing. I'm going to rewrite this now, filling in the blanks, so to say, right? So I've got blank minus blank plus blank minus blank squared. And I do this because it's really easy to get mixed up here and put the wrong thing. I'm going to put, this is my x1, y1. This is purely arbitrary. It'll work no matter how you designate these. So there's nothing saying that this has to be x1, y1, and this has to be x2, y2. You could switch those and you'd still end up with the same result. But for the first one, we want the two x's. So the first x I have, or the x2, is 3, so I'm just going to fill that in. In fact, I'll use a different color here so you can see that. The other x value is the negative 2, so I'm going to put that in there. Notice I'm being really careful. There's also subtraction here. And then let's go ahead and put in the y's. Since I designated this as my x2, this has to be my y2. So I'm going to use that, negative 4, subtracting 5. All right, so when we do subtractions with integers, so positive and negatives, it's helpful sometimes to change them to additions. And we can change that to an addition as long as we also change the sign of the number that follows that. It was a negative, so now it's a positive. So subtracting negative 2 is really the same thing as adding positive 2. That gives me 5 squared. Same thing here. I'm going to change that to an addition, but then this positive becomes a negative. This makes it simply easier for me to see that this is negative 9, and we're squaring that. So that's 25 plus 81, and adding those two together, that's 106, which if you take the square root of that is about 10.3 approximately. So that's the length of the line that connects these two ordered pairs. Where you really want to be careful is this putting it in there. So that's why I say, kind of put your subtractions in there, put some blank spots, and just fill in the numbers as they go. So it's easy to put, like, for example, we know that the second one was -2, so if I put in there a 2 in there, it kind of looks like a -2 because the minus sign is in front of it, but that isn't what I want to do. I've got to have minus -2. That's what becomes plus +2, which would be the opposite if I just had -2. I would turn that into plus -2, which is different than plus +2. So, at any rate, be careful when you're plugging those in. That's a really tricky part about using this formula. The next formula we're going to look at is the midpoint formula, which again, this is finding the midpoint of a line segment. So we're being given some actual points here, x1, y1, x2, y2, and we want to figure out what's the point that's right in the middle. And basically what we end up doing is we average out the x's and we average out the y's. We add the two x's, divide by the number of x's, which is 2, and then we add up the y's, divide by the number of y's, which is 2. So we're finding really the average x and y. And that should give us the midpoint. Let's take a look at some actual values here. So -3, +6 puts me up here. And 1, 4 puts me right here. And so here's my line segment. I'm going to use a straight edge here as I'm doing this. And let's go ahead and write that in there. -3, 6, and 1, 4. All right. So I'm going to go ahead and write out the formula. x1 plus x2 over 2. y1 plus y2 over 2. So filling these in with my x's, I've got a -3. Notice that it's plus. In this case, when we average, we add. So that's plus 1 over 2. And for my y's, I have 6 plus 4 over 2. So this gives me -2 over 2, and that is 10 over 2. So this is -1 and 5. So if I go up 1, or back 1, and then up 5, this would be the midpoint of that segment. Pretty simple. Average the x's, average the y's, and you have the midpoint of the line segment. All right. So where do these ordered pairs come from? Why do they exist? What use are they to us? Obviously, they're points on a Cartesian plane, but the point of an ordered pair is usually an ordered pair is representing the solution or a point that satisfies an equation. Such that when we plug those values into an equation, it produces a solution of the equation, which is generally just a true statement where the left-hand side is actually equal to the right-hand side. That's what a equation is. It has an equal sign. So it's a statement of equality. So frequently we can figure out a bunch. If we have an x and a y, there's usually a bunch of ordered pairs that are solutions. Many times we'll put our equation in terms of y, meaning y is equal to, we solve our equation, we get y by itself. And then we can put in some x's, and that helps us to find some ordered pairs that are solutions. And for many, many equations, the number of solutions are infinite. Unlike a one-variable equation, you have x plus 2 is equal to 4, then we know x has to be 2, right? It's the only number that, if we substitute it, will give us a solution. So in a lot of equations, there's like a single solution or a very limited number of solutions. But when we have, an equation that involves two variables, we end up with many times an infinite number of x's and y's paired together that would all be solutions, right? So, because a lot of times we're in the habit of solving things for y, we will sometimes refer to y as our dependent variable, because as x changes, we see y being affected by that. So in other words, y is kind of dependent, or the solution for y is dependent upon what the x is, right? So because of that relationship we tend to use, we will sometimes refer to the y as the dependent variable and the x as the independent. Whatever x is, we're going to put that number in, and then y is kind of dependent on whatever x input we have. If we put together a collection of all the solutions, usually it produces some sort of pattern that we can see in our graph, and many times that's what we're looking for. It's simply the collection of every ordered pair that satisfies the equation. So let's take a look at sketching a graph. And here we're given an equation. One thing that we're going to look at in future sections here is just patterns that we see with certain types of equations. Like here, we call this a quadratic equation. And quadratic equations tend to produce a certain type of graph. It's quadratic because y is being raised to the first power and x is being raised to the second. When that occurs, we have something called a parabola that forms. And a parabola is kind of a U-shaped, it's not really a U, it's kind of a cross between a U and a V. But generally it either goes up in both directions or it goes down in both directions. As either a high point or a low point that we call the vertex. And we're going to get more into that here down the road. But one of the ways to sketch, one of the most basic ways, is simply to pick some x values and then we look at the pattern, x squared minus 3, and then we find the y value that's paired with that x value. Actually, I'm going to rewrite this so it's a little bit bigger, so I have more space to work with. So x squared minus 3. We have our y outcome. Okay, so I'm just going to start with a few points, -2, -3, -2, -1, 0, 1, 2, 3, and see what we can come up with. So, I know exactly what I'm going to do each time here. So I'm going to go ahead and just write this out. And notice that where the variable is that I'm going to substitute, I put parentheses in its spot. Generally, that's a good practice as you're writing things out, to put a parentheses, and that's really to take into account negative and positives. So here, I'm going to plug in -3, this is -2, -1. These are the x values that I'm substituting into my equation. Now, because I put parentheses there, I wrote this out correct. This is why with negative numbers, parentheses are essential. -3 squared, if you type that into your calculator, you're going to get -9, because this square part only applies to what's directly in front of it. In other words, this is negative 3 times itself, which is -9. But with parentheses around that, what's directly in front of the squared is the parenthesis, and so that becomes negative 3 squared, which is positive 9, which is the correct, that's what we're after. We're squaring the input, and the input is a negative, so we want to square the negative. But if you just type negative 3 squared in your calculator, it's going to correctly give you negative 9. You actually have to use the parenthesis buttons on your calculator to get that result, positive 9. All right, so that's positive 9 minus 3, and 9 minus 3 is 6. And same with negative 2. Negative 2 squared is 4, and 4 minus 3 is 1. This is negative 1 squared, so 1 minus 3 is, negative 2. 0 minus 3, 0 squared is 0. That's going to give me negative 3. 1 squared is 1, minus 3 is negative 2. That's 4 minus 3, so 1, and then 9 minus 3 is 6. So in this case, I'm just going to plot these points out now. This is negative 3, 6, negative 2, 1, negative 1, negative 2, 0, negative 3, 1, negative 2, 2 and 1, and 3 and 6. So negative 3, 6 is up here. Negative 2, 1. Negative 1, negative 2. And 0, negative 3. 1, negative 2. 2, 1. And then 3, 6. And now we connect these with kind of a smooth curve. And again, you can kind of see this shape that we expected because we knew this was what we call a quadratic equation. And we have what we expected, which is a parabola. And that's the pattern that this particular equation gave us. And there are ways for us to make this a little easier. Kind of the key point here is this low point, which we call the vertex. We're going to look at how to find that vertex as we go forward. But for now, we're just looking at ordered pairs and how they connect to graphs. One of the other strategies we can use is to find the intercepts. And I talked about this near the beginning, where we look for where the graph crosses the x-axis, and where it crosses the y-axis. And what we saw in the beginning is that when y was 0, the value that resulted was the x-intercept. And when 0 was substituted for the x, the result is the y-intercept. And this is always the case. And so if we want to find specific points, in other words, the intercepts, we can substitute 0 in there, and that actually gives us, or becomes one of the easier things to find. So for example, here's an equation, and in this equation, they want us to find the x and the y-intercepts. So first off, we're going to look for the x-intercept. So we're going to put in 0 for y. Remember that the x-intercept, or intercepts, always have a 0 in for y. So plugging in 0 for y, I get this equation, x squared minus x minus 2 is equal to 0. So we have this 2-degree equation here. And one of the only ways that we can solve this, or one of the ways that we can solve this, is by factoring. Because when we have a product giving us 0, that tells me that either this would have to be 0 or this would have to be 0. In other words, if I have two things being multiplied giving me 0, either A or B must be 0. The only way we get 0 with a multiplication is if one of the factors is a 0. So, and you probably remember doing this. We have to have x here and here. To get a -2, for it to be negative, my signs have to be the opposite. And really, for 2, there's only one possibility or one set of numbers that multiply to give me 2, 1 and 2. I want a negative sum, so I'm going to put the 2 here and the 1 here. And my inners and outers give me -2x and 1x. Adding those together, we get -x, which is what we wanted, -1x. So, we look at the first and we say, okay, for this first parenthesis, what would x have to be to give me 0? Well, -1 plus 1 is 0, so -1. And here, what would this have to be 0? It would have to be a +2. So we actually have two places where this graph will cross the x-axis. -1, 0, and 2, 0. So I'll put that in there, 2, 0. These are the x-intercepts of this particular graph. And then we can find the other one. Let's see, I'm going to rewrite that here. It was y equals x squared minus x minus 2. So we already found the x-intercepts. They were at -1, 0, and 2, 0. So let's go ahead and write those in there. -1, 0, and 2, 0. Now let's find the y. So I'm going to substitute 0 in for x. This tends to be a lot easier. Again, I substituted. Sorry, let me redo that so I'm demonstrating for you the right way to do this. So I just rewrite the equation y equals parentheses squared minus parentheses minus 2, and then I substitute the 0 in there. Which 0 is really great. It's easy to figure out. 0 squared is 0. When we subtract 0, minus 2, so the result is -2. That's my y. So when x is 0, y is -2. So this is my 0, -2 would be right here. And so this is another point that we have. And if I was going to graph this, I at least know kind of where it's kind of centered around, where the vertex might be. I can plug in points close to that. So like I might want to figure out what 1 is. Because that's our next number there. I'm going to see 1 squared. So 1 squared minus 1 minus 2. That's 1 minus 1, which is 0. 0 minus 2 is -2 as well. So 1, -2. Knowing that the sort of pattern that we have, I know that between these, so like at 1/2, is probably my vertex. Probably the lowest point. So I'd want to plug in 1/2 and see what I get. That's 1/2 squared minus 1/2 minus 2. And so that's 1/4 minus 1/2 minus 2. So working from left to right, 1/4 minus 1/2 is -1/4. And subtracting 2, that's plus -2. So that's -2 1/4. So -2 1/4. That puts me right about here. So at any rate, we may want to try to find a couple more points, but we do have some points to go with here for our graph. That's finding the x and y intercept. And this can be used for any type of equation that we have. Symmetry is another thing that we look for in an equation. And symmetry means it's usually across some sort of linear boundary. And in this case, we have symmetry in relation to a particular line. So we labeled the line here L. That's the green line. And my points P and P prime are symmetric across this particular line. Generally, the idea of symmetry is you can kind of fold across that line, and these 2 points would match up with each other. So it's kind of like a mirror that we're looking into. We call it the axis of symmetry or the line of symmetry. So we're going to look at 3 different types of symmetries that we can check for. One is being symmetric about the y-axis, so the vertical axis. You can see here in this picture that if I folded this in half, right, across the vertical, that the 2 A's here would match up with each other. This point would match up with that point. This would match up with that. So on and so forth. So what we see is that, and some of my writing here is unfortunately covered over, but you'll notice that I have an xy here, so positive x, which yielded a positive y. When it's symmetric to the y-axis, the same negative x, so notice that x is the point on my x-axis here, right? So you'll notice that these are about the same distance to the right as it is to the left. So that's a positive x and the negative x. So we've gone the same distance to the left as we went to the right. When it's symmetric, the y value is the same. And that's if it's symmetric about the y-axis or the horizontal or the vertical axis, sorry. Same can be true for the x-axis. Similar graph here, but you can see that the same x, so I went to the right an x number, and that particular x yielded a certain distance up, which for the other point is that same distance but down. So a positive y and a negative y. So symmetry to the x-axis, x yields a positive y, and that same x will yield a negative y. And the last one is symmetry in regards to the origin, or the point here, 0, 0. So when we have symmetry in regards to the origin, 0, 0 there, the x, which gives us a certain y, would also, if I took the negative x, would yield us the negative y, right? So x, this is my distance x here. This is that same distance to the left, negative x. That gives me the negative distance, which is equal to the positive distance here for the y. So for every point xy, the point negative x, negative y is also on the graph. That's what this this covered up thing says. So to sum those up, our tests for symmetry, the graph of an equation is symmetric about the y-axis if replacing x with negative x results in an equivalent equation, results in the same output, the same y. The reason why we say the equivalent equation, I can just kind of replace that with y, is that most equations are solved for y. So y equals ax plus b, this is our linear equation. If we put an x in there, and then a negative x, does it yield us the same exact looking expression, ax plus b? It wouldn't in that case. Okay. Equation is symmetric with the x-axis if replacing y with negative y results in, again, an equivalent equation. And the last, it's symmetric with regards to the origin if replacing x with negative x and y with negative y results in a similar equation. So let's do some checking here. Here's our equation. We have a rational equation here that involves a fraction. Any equation that involves a fraction with x usually in the denominator, we call that a rational equation. So we're going to first check for symmetry to the x-axis. Or no, I'm sorry, let's do the y-axis first. That was the first one on my list. And that's what's there as well. Let me go to my next slide. Yeah, there. Okay. So we're going to do this for each one here, even though it just says to the y-axis. All right. So with the y-axis, xy and negative xy should be the same. So I'm going to take x and put it in there. Well, x put in there gives us this equation. So let's put negative x in there. So y equal to 1 over negative x squared plus 5. Well, what is negative x squared? Again, using the parenthesis there, if I have that in parentheses, that just will become the same as x squared. Anything squared becomes positive. And so, yes, here we have symmetry with regards to the y-axis. Let's try the x-axis. For x-axis, x, y, and if we put in a negative y, we should also get the same x, so the same equation there. Well, if I substitute in negative y here, I really don't have the same equation as I did before. Generally, with a negative y, and we generally want to solve for y, I would multiply both sides by negative 1 to make that positive y, and then I would have negative 1 over x squared plus 5, which is not the same thing. So we would say this is not symmetric to the x-axis. And then for the origin, x, for every x, y that we have, there should also be a corresponding negative x, negative y. So in other words, if I substitute negative x and negative y, I should have the same equation. But of course, when we plug this in, let's see, negative y equal to 1 over, remember it's negative x squared plus 5, negative x in parentheses, that becomes positive x squared plus 5, again multiplying by negative 1 on both sides to get rid of the negative over here. At least with the same thing, negative 1 over x squared plus 5. So that's an altered equation. It's not the same as my original. And so we would say this is not symmetric. I'm just putting x as in, not symmetric in regards to the origin. Okay, so again, let's try this with one more equation. Looking at the symmetries here, I'm going to do the x-axis, the y-axis, and the origin. I said those backwards, but so starting out with the y-axis, notice that with the y-axis, when we test for that, we're substituting out positive and negative x. For the x-axis, we're substituting out positive and negative y to see if we get the similar or same equation. And for the origin, we're substituting substituting out negative and positive, negative x and negative y. Okay, so again, here we go. Y equal to 4 times negative x minus negative x cubed. Notice this gives me negative 4x, and then minus, this stays negative, so minus negative x cubed, which becomes plus positive. So notice here, when I substituted in a negative x, this is not the same as my original equation, which was 4x minus x cubed. Now I have negative 4x plus x cubed. Not the same. So not symmetric in regards to the x-axis, or y-axis, sorry. All right, for the next one, we're going to substitute out positive and negative y. So negative y, and then the x's remain the same. 4x minus x cubed. Well, again, if I was to get rid of that negative y, I would multiply both sides by negative 1. That negative 1 goes to both parts. So this would give me positive y equals negative 4x plus x cubed. Again, same thing happened here. I got the complete opposite. Instead of positive x minus x cubed, I have negative 4x plus x cubed. So not symmetric in regards to the x-axis. For the origin, I'm going to substitute negative y and then also negative x. So for negative x minus negative x cubed. So I have negative y equals negative 4x plus x cubed. That minus negative raised to the third power, it stays negative. So I have a minus negative, which becomes plus positive. And getting the y to be positive, we distribute a negative 1. That gives me positive 4x minus, the negative 1 here changes both sides there, so minus x cubed. This is the same, and so yes, we would say this particular equation is symmetric in regards to the origin. The last thing we want to look at is the graph of a circle and what its equation looks like. And of course, you all know what a circle is, but when we have a circle, in a technical sense, we have to have a center someplace. And so we label the center of that circle as being at HK. Now, the center, ironically, is not actually a point on the circle. The center point is just a point about which the points lie, right? The points that are actually making up the circle. But at any rate, we use H and K to represent kind of the center there of that circle. And then that center that we have, wherever it is, we'll have a set of points around it that are all equal distance from that center point. This is a terrible graph that I've drawn, but hopefully you get the idea. We call that the radius. It's the fixed distance r that all the points of the circle are from that center. And this is actually what we call the standard form of the equation of the circle. Notice y minus h is the x part of the center, and y minus k, which is the y part of the center. Those are squared added together, and that gives me the distance from the center to each point squared. Kind of very Pythagorean, isn't it? Kind of like what we saw before. There's a relationship there. So again, here's just sort of some more pictures drawn here for this. Our center's at hk, so x minus h squared plus y minus k squared equals r squared. R is the distance from the center to here. H and k, of course, K is the horizontal distance, H is the vertical distance. I'm sorry, I said that backwards actually. K is the vertical distance and H is the horizontal distance. Okay. So find an equation of the circle. Let's say that we know that the center is at 7, -3, and that we're passing through this point. The circle actually passes through that point. Okay, yep, I'm going to go back here. So one thing that we need to know is the distance. We know we've got a center. I'm just going to draw a quick little sketch here. We're at 7, so 1, 2, 3, 4, 5, 6, 7. 7, -3. So I'm going to go down 3 units here. I'll try to erase this. And I just want to draw in the center here. Excuse me. And then I have a point that I know is on the circle, 5, -2. So let's go ahead and draw that out too. 5 and -2 would put me right here. So this is my HK, 7, -3. And this is 5, -2. So what I need to know is the distance between these two, right? Because that distance is going to be my radius, r. And then from that, if I were to rotate that thing around, it's going to give me a whole set of points that make up my circle. So the first thing I need to do is to find the distance. Here's where we can use that distance formula. We know that the distance will be my two x's subtracted, so blank minus blank squared, and my two y's subtracted squared. Plugging those in, my x's are 5 and 7, and then my y's are -2 and -3. We're going to make that a plus, change it the sign, make that a plus, change the sign of the number that follows it. And now simplify this down. 5 plus -7 is -2 squared. And then -2 plus 3 is actually 1 squared. So this is the square root of 4 plus 1, or the square root of 5. That's the actual distance here. That's my r, square root of 5. So let's take a look and go back to that formula where we had x minus h squared plus y minus k squared, h and k being the center, is equal to r squared. So I'm going to leave those blank spots there. H and k. We keep the x and y because we want to keep those variables. And we have r squared. And somehow I had a plus there, so I'm going to turn that into an equals. Square root of 5 squared. And so here's the equation of my circle. X minus 7 squared plus y plus 3 squared equals square root of 5 squared, which is simply 5. Notice that what we end up seeing here, right, my center was at 7, -3. But whenever we put in values after a minus sign, what we end up seeing is the opposite of what the actual center's at, right? I have x minus 7 squared, and my x value of the center is positive 7, and I have y plus 3 squared, and the y value is the opposite of that. And in general, whenever we have formulas that have a minus in front of the variable, when you're trying to interpret the value of that variable, you want to actually look at the opposite sign, because subtraction kind of makes it the opposite. Okay. The last part here, we're just going to do some graphs. And you'll notice here with x squared plus y squared, there is no h and k. It's just x squared and y squared. Well, that tells me that 0, 0, actually, the h and the k are both 0. So we have our center at the origin. And if this is my r squared equal to 1, then r will be equal to the square root of 1, which is also 1. And so that's my radius, and that's how I was able to draw this. I went out 1 in the 4 directions away, and then I just kind of connected the points. Now, the actual circle itself is just right here. The center is not really a part of the circle, is it? No, it's just the points around the center. So the center is more this kind of invisible thing. All right, for this one, we definitely have an h and a k. And again, looking at this, we want to think opposites. X minus h is the general formula. So if I have x plus 2, and this is the general formula, then I need an x minus negative 2 in order to get x plus 2, right? Because x minus negative is the same as plus positive. So my h is actually negative 2. And if I have y minus k, and I have y minus 3, then we see that k is actually positive 3. So notice again, x plus 2, my h is negative 2, y minus 3, that tells me my k is actually positive 3. So negative 2, positive 3 puts me here. And r squared is 25. Taking the square root, r is equal to 5. We just take the positive rather than the positive and negative. But 1, 2, 3, 4, 5, that's one part. 1, 2, 3, 4, 5. And then back 5, 1, 2, 3, 4, 5. Down 5, 1, 2, 3, 4, 5. Again, a circle is one of the harder things you'll ever have to draw. Say if you're a expert drawer, if that's a word, illustrator, you can draw a perfect circle. I certainly am not one of those, and please excuse the line going across the screen there. I can't really do that without erasing everything. At any rate, this gives you an idea of some of the homework problems you're going to be working on, and good luck, and we'll see you in class.